Hello and welcome everybody to the fourth and final video in our proportional reasoning unit. Today we're going to look at scale factor and three-dimensional figures. If the scale factor between two similar figures is a to b, meaning some number, so what I'm talking about is instead of a to b, I could say here, example, 2 to 3, okay? Which means it's like 2 units in one. So 2 units in this first object is like 3 units in the second object. That's what that means. The ratio of their surface areas is then a to b squared. Another way of writing that, now I've kind of pooched myself here by writing it the way I did, but oh well. I could also write that a squared to b squared. So with my example, that would be then 2 squared to 3 squared, or 4 to 9, which again means the same thing. That would be like 4 units in the first shape is like 9 units in the next shape. And then with volume, the ratio of their volumes is a to b cubed, which we can then write as a cubed to b cubed. You can also write these as a fraction, so I could write it like that. And then my example, it would be 2 cubed to 3 cubed, which is then 8 to 27. And once again, it means that's like 8, and if I gave it a unit, maybe 8 centimeters cubed in object 1 is like 27 centimeters cubed in object 2, and that's how they relate to one another. So let's look at some examples using this scale factor. So in example 1, given 2 cones with radius 3 centimeters and 2 centimeters. So I could draw that down here. Okay, so the radius is 3 centimeters for this guy, and then a radius 2 centimeters for that one. Now I drew those really quickly, but just to give you an idea what's going on. So what is the ratio of the surface areas of the cone? Now, often what they'll say, or what a question could say, is it'll direct you a bit and say larger to smaller. So why don't I add that in? Large to small. Because your scale factor can be written either large to small or small to large. It's a relational idea, so there is no proper or perfect way to put it. It's usually just specified in the question. So what is the ratio of the surface areas? Again, so we have to start with the scale factor. Our scale factor, if I'm going large to small, is 3 over 2. For the surface areas, the surface areas of these objects are related by squaring your scale factor. So I'm going to square it. So then my scale factor squared is equal to 9 over 4. So you could express that as a fraction, like I said, or as a ratio like that. But what it's saying is that 9 centimeters in the large cone is like 4 centimeters in the smaller cone. What is the ratio of the volumes of the cone? Okay, and again, we're going to work from large to small. I could also go small to large. It'd be the same answer, just it'd mean a little bit different, obviously, if I was going small to large. But again, we start with our scale factor, 3 over 2. So again, to find that scale factor, you just have to find 2 corresponding measurements or corresponding ideas. Like it could be 2 areas if they gave you the areas. Anyway, to find the ratio of their volumes, we cube our scale factor. So the scale factor cubed is equal to, well, 3 cubed over 2 cubed, obviously, which is then 27 over 8. And again, I could express it like this, 27 to 8, however you want to do that. Both of these are acceptable. If you're working with a proportion, however, you're going to always choose the fraction because that could be the left side of your fraction. And for understanding again, this means that 27 cubic units in the first cone is like 8 cubic units in the second cone. Part C. If the surface area of the larger cone is 360 centimeters, what is the surface area of the smaller cone? Okay, so they're dealing with surface area, and they're wondering if we know the surface area of the larger one, what's the surface area of the smaller one? They're similar, so therefore they should be related. Well, we'll use a proportion. Okay, so I'm going to have my proportion, this equals that. And again, on this left side, I have to come up with some sort of math fact. The math fact is going to be have to do with our scale factor. So we know our scale factor is 3 to 2. We're talking about surface area, so we already talked about this, that we'd actually have to square our scale factor. So our scale factor squared is 9 over 4. This is nothing we don't know. So then I'd put that into my proportion, 9 over 4. And I have to remember that I've gone large over small. And the reason I want to just note that is that in my second fraction, I have to make sure I do the same thing, large over small. So it said the surface area of the larger is 360, so that means that 360 has to go on top. My x goes on the bottom. And now I can solve this proportion, and I'll know the surface area of the smaller cone without actually having to go through my surface area formula to determine it. Because I could do that as well. If I had more information, I could simply figure out what the surface area is, because the surface area of a cone, the formula is pi rs plus pi r squared. I could go through that, but this is a shortcut if I have this information. Anyway, back to this. 9 times x, 4 times 360. So 9x equals 1,440. Go ahead, divide this by 9. 160, and then whatever units I'm talking about, it's centimeters, so centimeters squared. So that means the surface area of the smaller cone is 160 centimeters squared. D, if the volume of the smaller cone is 152 centimeters squared, it should be cubed. Sorry about that, guys. That's cubed. What is the volume of the larger cone? So they're talking about volumes. So again, I could use my volume formula to find the larger cone's volume, but I would need to know a few more details. Like I only have the radius right now. I'd need that. I need the height. So I'll have to use scale factor, which is okay thing to do. So 3 over 2. I'm going to cube this though, because remember the volumes are related by cubing your scale factor. So 27 over 8, and again we figured this out before, but now I use this in my proportion. So 27 over 8 is equal to, and again I put the larger cone on top. So the information they told me was the smaller this time. So now I can find the larger cone's volume without actually calculating it, just by using this proportion. So 8 times x. 27 times 152, so 8x equals 4,104, divided by 8, divided by 8, x is equal to 513, and that would be centimeters cubed. So the volume of the larger cone is 513 centimeters cubed. Okay, example 2. Mr. Troy bought 2 sizes of spherical containers from a craft store to make decorative candles for Christmas. The diameter of the small spherical container is 3 centimeters, and the diameter of the large spherical container is 5 centimeters. If it takes 113 centimeters cubed of wax to fill a small container, how much wax would it take to fill a large container? Okay, so what I'm getting at, I was thinking about making these circle or spherical candles, ball type candles. So spherical container, that's just kind of, I'm trying to make a ball type container or a ball candle. And in this first one, it's the smaller one, its diameter is 3. In the larger one, the diameter is 5. All right, so just to give you a bit better picture of what's going on. So they're talking about how much wax would take to fill. So if you're talking about how much liquid or how much it would take to fill the object or how much space it would take up, we're talking about volume. So we're going to work with volume here. And now I don't have enough dimensions on the larger sphere to calculate the volume directly, so I have to use scale factor. So what would my scale factor be? Well, remember your scale factor is equal to the 2 corresponding dimensions, and you can reduce it if you wish. So I have these diameters, so that they're corresponding to each other. So I can go 3 over 5. If you wanted to go 5 over 3, you could as well. It wouldn't matter. It slightly means something else. Like in my scale factor here, it says 3 over 5, so that means that the small ball is on top, meaning it's 3/5 the size of the larger one.
Could Alex pass, please?
If I would have wrote it as 5 over 3, it would simply mean that that larger ball is 1 2/3 the size of the smaller one. Anyway, so that's our scale factor. That's our basic scale factor. Now we're dealing with volume, so we've got to cube our scale factor to get that ratio we need, because the ratio of the volumes is equal to the scale factor cubed. So scale factor cubed equals 27 over 125. So that's the value I'll use in my proportion. Whoops, 27 over 125. Now I put the small ball on top, and it says here it takes 113 centimeters cubed of wax to fill the small one. So that's 113 goes up here, and I'm wondering about the large one. Again, I could find the volume of the large one myself if I had the proper dimensions, but I don't have enough information, so that's why I'm forced to use scale factor. So 27 times x, 125 times 113. Sorry if some announcements kick in, everybody. I'm at school here doing this one. That is 14,125. Divide them both by 27. I'll put this up here. So then x is equal to 523, and then some decimals. It says to the nearest hundredth, so 2 decimal places, 15 centimeters cubed. So that's how much wax it would take to fill that larger spherical container. And there you go. That's everything I got for this scale factor and three-dimensional figures video. I hope it made sense. If it didn't, get talking to your teacher or get into contact with myself. Have a great night, everybody.